Okay, welcome back. What I want to look at today is capacitance. Now I'm using work from Mr. D. Dunn. Okay, I'll see his name at the bottom here shortly. But okay, and this is what we want to look at today: capacitance. Yeah. Now I would love to have colored you in, but I can't do that, so I got to use you as you stand. Okay. So let's look at the introduction. Capacitors are two terminal devices which are used in DC and AC circuits. In this case, in this outcome, we shall be restricted to the theory and construction of capacitors and DC applications. Okay. Capacitors can be used to do the following: store static electricity, store electrical energy, block the flow of direct current, finally allow the flow of AC. This is the gentleman I'm looking at, okay, thanking him for his work, DJ Dunn, okay. I don't know how this is going to come out, but I'm hoping that it works, comes out as I would like it to come out. Now, basic theory and fluid analogy. This I'm not going to read for to you, okay, but I will expect you to read that for yourself. Okay. And here all we're looking at is the reference between the pressure in a container and the pressure in the capacitor. The capacitor holds the voltage when it is charged, and when you put a resistor between it, it will discharge. Now you cannot touch the two terminals of the capacitor open-endedly, otherwise you will receive an electric shock, which could be fatal. And here we're looking at two plates, which is here we have your dielectric, okay? Consider two plates each with an area A and separated by a distance D. The material between them is the dielectric. The charge Q stored on a pair of plates depends upon the voltage and the physical dimensions and properties of the plates. And the dielectric. For a given capacitor, it is found that charge is directly proportional to voltage such that Q equals C times V. And here you are, Q equals C times V. Now I don't know if it's going to come out any good at all, but I'm going to continue, okay? Now remember, the farad is a large unit, so we deal in microfarads. F to the minus 6, okay? Nanofarads and picofarads. I'm just wondering if I could. Now here, work example, capacitor stored 0.05 coulombs. When the terminal voltage is 160 volts, what is the capacitance? And here you have your value of capacitance at 312.5 microfarads, okay? So what is happening here? They move the decimal point 1, 2, 3, 4, 5, 6 places in order to bring it 10 to the sorry, make sure I said that right, 10 to the 10 to the minus 6. It's okay. So I had something else in mind. Okay. Right, now this here is for you to begin to work yourself. E equals CV squared over 2. Right, these are values for you to work out for yourself. I'm not going to work them out for you. I think these are things that you need to write out and apply. Okay, this is how a capacitor looks like. It's rolled. Okay, so this here paper, plastic, metal is actually this. Okay, so be aware of that. I don't know how this is gonna roll. I'm gonna have to look at this in a. Okay, you have different types of capacitors here: silver, mica, ceramic, tantalum, bead, electrolytic. You have variable. Okay, you have the symbols for each there. Okay. Okay, you could do this as an experiment, okay, but obviously be careful any experiments you do at home, okay. And with this, something you'll normally do in the workplace. What happens is that the light is meant to come on when you actually switch the capacitor. After charging the capacitor, you switch the capacitor to a terminal point, which should actually bring the light on. I have to admit, I haven't actually done this experiment myself, so this is power supply and you have a joule meter. Now the resistor is to allow the capacitor to discharge slowly, okay, and to make sure that it is dead when you come to touch it or come into contact with it in any form. Now again here, make sure the time constant okay, T equals R times C. Now again here, now the meaning of the time constant again here is for you to read for yourselves and to, one second, let me make sure I can put this into, okay. I was just concerned it might not be in frame. Okay. And here's your work example. Okay. And here it's simply showing you the electrostatic theory to make sure you're familiar with that, with these items. E equals V over D, D equals Q over A, etc., etc. Okay. Now most of you should be familiar with absolute permittivity, etc., and relevance of free space. Okay. Here we have another work example, so make sure you can understand it and write it out in full, okay? Capacitors, okay, in parallel, okay. It tells you now. Here you have capacitors in parallel and capacitors in series. Make sure you become familiar with how they are calculated, okay? Now here it's important to remember that when you're dealing with capacitors in series, you're applying the technique that you would use for parallel resistors. That's the method that you would apply for that, okay? Whereas in parallel, you will simply apply that, you will simply add them as you would for series, okay? But make sure that you write up this for yourselves, make sure you understand it, and you don't just try to take it off the screen, okay? Here are some exercises for you to do. Have got those as well. Here's some self-assessment work for you to do. Okay, so please try and complete it. Okay. And again, thanks to Mr. DJ Dunn for the work that he's done. Okay. I'm just going back, making sure that I've got everything in place. Okay. I don't know how this is going to come out yet, but it's interesting to see. Okay. Okay, and we're back to square one. Okay, and thank you. I hope you found this useful. Have a good day. Bye bye.